Yeah, I'm really happy to introduce Professor Michael Koehl from the University of Bonn, who also flew in yesterday.
Yes.
Yeah, so another person who we should thank a lot for coming such a long way. So thank you very much.
Thank you very much. First of all, thanks for the invitation and for organizing this meeting at this beautiful location. It's my first time here, but it looks really marvelous. It's good. So
we like it.
Yeah. So in my lectures I will introduce you to get a different type of quantum system, namely Koehl's trapped ions, and how to interface them with other quantum systems. And this will be called atoms on the one hand, and semiconductor quantum dots on the other hand. So in this lecture today, I will give you a sort of first introduction into ions, ion trapping, ion manipulation. And just like the previous speaker, I will not spare you any detail, but I will try to take you through all the details of how to trap an ion, how to manipulate the ion, to give us a firm basis then for the experiment in the next lecture. So my background is basically in ideal quantum systems. And ideal quantum systems are really well isolated from the environment. We don't like decoherence. We don't like environmental effects, but we cannot control them. So we need to protect these systems very well from the outside world. We would like to have stable quantum states, so states where we can take measurements from one particular, if we do high precision measurements, the states have to be long enough in order to get to the required spectroscopic resolution, for example. You want to have good coherence times, so the internal quantum dynamics of the system needs to be well controlled, which in part goes together with the insulation from the environment, but also the intrinsic decoherence mechanism should be small. They should be well observable, particularly if we talk about individual quantum systems. This is a big challenge. We want to see single atoms, single ions, and we have to make sure that we actually have enough signal to noise in the detection to see that. They should have low cost. I mean, we talked about diamond before. Now we're talking about small lumps of metal. I'm not saying that the overall cost of the experiment is cheaper with ions. But if you talk about just the samples, they're slightly And maybe the most important thing is we want systems that have reproducible properties. So if you want to make an experiment one day with one sample and next day with another sample, we want to see the same result. So we don't want to rely on any external manufacturing procedures, so that we really have every day exactly the same samples in our experiment. And well, the conclusions from this, or one of the conclusions with this is, well, you could work simply with a single atom. Atoms fulfill all of these properties, but then we're left with the problem, okay, how do we trap them, how do we control them, and how do we manipulate them? And but before I go into these details, I would like to go back to this quote from Schrödinger from the 1920s, probably. It's in German originally, but I put a translation here. Basically, his statement was that he cannot imagine that we can ever experiment with single particles, just in the same way that we cannot recreate or breed any dinosaurs at the zoo. We don't know what this ichthyosaur is. That's it. And it lived probably hundreds of millions of years ago. And the reason why we can't read it basically is that it only exists in this form today. And so basically his idea is sort of, or his point was that if you want to go there from a living creature again, that's even harder than trapping single atoms.
Sure, we did not watch Jurassic Park.
No. No, we didn't. Okay, so and basically since the birth of quantum mechanics, people have dreamt about doing experiments with single particles because these are the ideal representations then of this theory. There are quite a few questions, basically how to trap a single atom, how to observe it, how to isolate it, and then in the end, what to do with it. For trapping, we have a number of forces available in nature. We can trap them electrically if they're charged, magnetically if they have a magnetic dipole moment, optically. We can put them in a crystal, as we've seen in the last lecture. So there are many options that we have in principle. How to observe them? Same, there are many options. So we can have fluorescence detections with lasers, but we can also just ionize them and then measure the charge on a single electron multiplier, or even capacitively, if you put them in front of a capacitor plate and modulate their position, you can see the induced charge in the capacitor plate. All of this has been done by now, and these are just basically some options. Well, how to isolate them? Well, the best thing, obviously, is to put them in an ultra-high vacuum where they are shielded from all environmental influences, but also we can put them in crystals, as we've seen in the ND centers in London. What to do with them? Well, today we do quantum information processing with these systems if we have them at hand, because the non-coherence time really favor the application of gates and quantum computation of these isolated quantum systems. But also they're important for precision measurements like atomic clocks, and increasingly more so also for sensors, quantum sensors for magnetic fields, for electric fields, maybe gravity and so on. And in particular, in the view of this workshop or this school here, the question is, of course, how can we couple such individual systems then to other quantum systems again, to potentially have even more use of these combined systems. So we want to discuss how we can go for this hybrid approach. So trapped ions basically are electrically trapped particles that are charged and then trapped in electric fields. We observe them with fluorescence, and they're trapped in ultra-high vacuum. So this is basically the area of techniques that we want to go through in the lectures. So the overview, as I said earlier, there are 3 lectures. The first one is the basic physics of the single trapped ions, how to trap them, how to manipulate them. The next one will be then on hybrid systems of trapped ions and neutral atoms. So when you combine quantum generate gases with single trapped ions, we can see a lot of interesting chemistry. And then the last part, I will talk about how we can interfere or couple to very different quantum systems, namely trapped ions and semiconductor quantum dots. And I will show you how we can overcome the bandwidth mismatch between these two systems. Right, today, so we talk about the single trapped ions. And the overview of the lecture today is well, the introduction we've just had. Next, we will talk about the physics of the Paul trap, the radio frequency Paul trap, where the singles ions are contained in. Then we will talk briefly about the laser cooling of the trapped ions, and then some basic manipulation and detection techniques of how to prepare certain quantum states. So, if you want to trap a charged particle with electric fields, you're facing basically the following problem. Suppose you have 2 electrodes here. They're both charged to some voltage, it doesn't matter which one. Now here's positive, and you put a positive charge in the center between these 2 electrodes. This charge basically experiences a saddle point potential. It is repelled from these electrodes, so it is not going anywhere near these electrodes, but at the same time it is forced outwards into the radio plane. So the potential approximately looks like this. And this is a very fundamental result of Schrödinger's equations. You have divergence of E is 0 in vacuum, and divergence of E of 0 basically means if you take a small volume around a single ion, you have as many field lines going into this volume as you have coming out of this volume. The force is always along the field line, so there is no net force leading into the small volume in space, free space. So basically we cannot stably trap a single charged particle with static electric fields in vacuum. And this was known, of course, since actually even before Maxwell's equation. This is called Earnshaw's theorem, which was derived by a graduate student in Cambridge in the UK a few years before Maxwell set up his equations. And then in the 1950s, Wolfgang Koehl from the University of Bonn came up with the idea, well, if it doesn't work with static electric fields, why not try alternating electric fields? And so basically his idea was, if you put a particle here, charged particle here, it experiences the saddle point potential, so it will be confined in this direction, it will be deconfined in the other one, and so it will start traveling down the hill to either of the 2 sides. But if then the particle has traveled a little bit, and you now flip the sign of these voltages, so you go to this configuration, then the saddle point basically flips over. And now in the direction where the particle previously was deconfined, it now sees a confining potential. And so if you do this with the right frequency, his imagination was that you can dynamically stabilize a particle here at the center of this potential. He tried that out, it worked. He got the Nobel Prize in Physics for this in '98. And we will now basically walk through how this trapping mechanism actually works. It's a little bit more sophisticated than this very simple explanation. Okay, so what happens to a single charge in an alternating potential? Here's the equation of motion. Acceleration is q times the electric field. Now this electric field is oscillating with the frequency capital omega, which exerts instantaneous force on the ion. And since this is a harmonic oscillation here, this eventually will lead to a driven harmonic motion of the single ion. Very simple. Now, the point is, what we have to understand is what happens to this particle on a slow time scale, namely on a time scale that is much longer than the oscillation period of this force. So can we maintain the particle at this location even in the long time scale, so averaged, or at least over a time of 2 pi over omega. And if this force is, if this electric field is homogeneous in space, this force averages to 0, right? Because the cosine nicely averages to 0, and there is no net force being left over. And so this principle does not work. There's no trapping if the electric field is homogeneous. Now let's look at an inhomogeneous electric field. So we now take some variation of the electric field, and we take the ion to some equilibrium position, R0, and then look only at the fluctuations around that equilibrium position. And we take this ansatz, we put this into the previous equation of motion, and then we get the appropriate equation for this small perturbation to the electrons or ions equilibrium position, which is given here. And we see from this that the excursion of the ion instantaneously follows the electric field. So there's sort of, it has the exact e to e naught times cosine omega t dependence, but it's out of phase. So it requires a minus sign here. So the ion oscillates exactly out of phase with the driving electric field, which is good because this means that the force driving the particle is exactly out of phase with the response of the ion, and sort of not continuously pumping energy into the system. On the other hand, you see also that the amplitude of this oscillation depends on the local electric field strength. So if you look at an inhomogeneous electric field, as depicted here, and we look at 2 different locations, out here the field lines are more widely spaced, so the local electric field strength is less, so the oscillation amplitude is less. Here the field lines are more dense, local electric field strength is higher, and the amplitude of the oscillation is higher. But it's always exactly along the local electric. Okay, so how does this help trapping? Okay, so now we do a little bit of maths. We take our inhomogeneous electric field, we do a Taylor expansion to first order around this equilibrium position of the ion. So this is here, so this is a vector field, and we have to do this in 3-dimensional space, so we need this Jacobian here. We can then re-express this into this convenient form, so we have delta R, that's the displacement, times the gradient operator times the electric field. Okay, now we can compute the average force. The average force is just now this electric field times the charge, averaged over 1 cycle of the oscillation connection. So we put in our Taylor expansion here, we put in this solution here for the small excursion of the ion, how it instantaneously reacts to the electric field. There, do a little bit of maths. We see the first term here from the homogeneous field that drops out because the integral over cosine is 0 over 1 oscillation period, and this part over here, there we get the cosine squared because we have the cosine of the driving field times the cosine of the response of the atom to this cosine squared, and this gives a constant. So there is a force left over in this inhomogeneous field, which only comes with this term which has a gradient or the inhomogeneity of the electric field. We can then again use the rules of vector calculus to re-express this as a gradient of electric field squared plus this term with the rod. The rod is 0 from Maxwell's equations. And then we end up with this marvelous expression here that the time average force over one cycle of the motion is just a prefactor which depends on charge, mass, and driving frequency, and the gradient of the electric field squared. Okay, so this is some maths, but which, if you want to go through this more slowly, I'm happy to give you the slides. But the result is quite astonishing, because the result shows that the time average force that we have on this particle can be written as a gradient of something, namely the gradient of what is called a pseudo-potential. So remember, we don't really have a potential there because we have a time averaged problem. But from the momentary reaction of the ion to that driven problem, we can actually write this down as the force as a result of a gradient of this pseudo-potential here, which is basically the charge times the electric field squared, or is proportional to the intensity of the electric field, divided by mass in ohms. This is quite remarkable. This was found by Dehmelt, or this description was derived by Dehmelt in this clarity, and I think this is really a remarkable result. And actually, this holds for many of these driven systems, and this is generally called a quantum-remotive force. The way how you can think about this, basically, is the following. If we go back to this slide here. So at this location here, the velocity of the local velocity of the ion is the displacement times the driving frequency. So here, the kinetic energy, mv squared of the ion, is higher than here of this driven motion. And this increase of kinetic energy acts like a potential. This is up to a factor of 2 or 4 or so. This is exactly what this pseudo-potential gives as the potential energy. Okay, so this is basically how this trapping mechanism works in this inhomogeneous oscillating fields. Okay, so in order to construct the trap, this means we have to find an electric field configuration which has an intensity minimum, because the ions are attracted to the intensity minimum of the electric field, and sort of the straightforward example of this is the electric quadrupole field. This is the standard three-dimensional quadrupole, x, y minus 2z squared. You immediately see that this fulfills divergence E equals 0, and has some prefactors, basically the voltage divided by the distance of the electron of the ion to the electron. And the quadrupole field is realized basically by electrodes which have hyperbolic surfaces, and basically the original arrangement, this is actually from Paul's Noble lecture, is shown here. So you have two so-called end cap electrodes which have these hyperbolic surfaces, and the ring electrode, so this is just cut open, the ring electrode also has hyperbolic surfaces, and between them you just apply the oscillating voltage. This creates the quadrupole, and this traps the ions at the center of the position. And this quadrupole potential here, which is sort of linear in the electric field, is quadratic in the pseudo-potential. So we have a harmonic pseudo-potential in which the ions are trapped. So we can really think of the ions as being in a harmonic oscillator. Okay, so far so good. Now the big question is, how fast do we actually have to oscillate this? And the reason why this question is important is it's straightforward to see that the two limiting cases are quite problematic. If we go for omega to 0, then the trap becomes static and unstable. And if we go with omega to infinity, then the pseudo-potential goes to 0. Basically, we flip this up and down so fast that the average potential is just flat. So we see that none of these two extreme cases works, and the sweet spot somewhere is in between. And now in the next few slides, we want to understand how we can find where the sweet spot is, where this works. So we need a slightly more elaborate treatment than just this pseudo-potential approximation that we had previously. Okay, so for this, this cannot be solved in fully generally here. So we go now for a specific example, which is the so-called linear quadrupole trap. So I showed you earlier the example from Koehl's noble lecture of the trap which was completely enclosing the ions. This is nice, it works, but it makes it very difficult to actually see anything because the ion is completely surrounded by electrodes and there are very few gaps where you can observe it. And that's why people have then moved on to more open geometries where you could actually see the ion, but which still approximate the hyperbolic surfaces basically. And one example here is the linear quadrupole trap, where you have basically 4 electrodes, which are, well, ideally infinitely extended rods, which are then supplied with this alternating voltage. And they provide the quadrupole potential in this plane, in the XY plane. And in order to have any confinement along the Z direction, you just put DC end cap electrodes on either side. Okay, so for this specific example, we can write down the electric potential. So this is really the electric potential, not the Tudor potential, which has the driving voltage here, plus an optional DC voltage on the electrodes. And this is the potential of the pure quadrupole. Then we have an additional DC potential from these end cap electrodes, so they're both charged up to some usually positive voltage. And near the symmetry point between these two electrodes, we can approximate this again as a harmonic potential. So it's harmonic in Z, so Z squared. That leads to an anti-confinement in X and Y, and this is again due to Maxwell's equations. The divergence of E has to be 0. Okay, so we write down the equation of motion as the gradient of the potential, and then we can try to solve this. Now, in order to solve this, we go to some scaled coordinates, which makes the maths more visible. So we scale our time with the oscillation frequency to form this parameter psi, and then we have 3 parameters which include all the voltages, the masses, the frequencies, and so on and so forth, which are dimensionless. Okay, and when we write this down, then we get this set of these 3 equations. And those of you who have seen those before, you may remember, these are just Mathieu's differential equations. The Mathieu equations are very well studied for any kind of driven systems or periodic systems, also for band structures of lattices, where this is not a time variable but a position variable. And we know the solutions of Mathieu's equations, or at least no, we don't know all the solutions, but we know how to solve them. Let's put it this way. So the very general solution is hard, but here we do this sort of in a pedestrian approach, in a just power series expansion with in powers of e to the I omega t, which is basically like a flow K type solution to this problem. And we do this only in lowest order of omega. And if we do that, then we see that we get this expression for the solution for the x coordinate, and similar for y and z. And what we see from that solution is that we have 2 superimposed oscillations. One at the driving frequency, which is high. Omega is the fastest frequency in our problem. And one slow oscillation here, which on top of that with the frequency omega x. And this omega x is given by this parameter here, beta x times omega over 2. Beta is usually a very small number and is related to these coefficients up here. But beta is much, much smaller than 1 for almost all purposes. So typically you work in a range where beta is maybe 10 or 20th or 30th. So we have 2 superimposed oscillations, one very fast one and one very slow one, which describe the motion of the ion in this time-dependent potential. So here is sort of the graph of how this looks like. So we have this very fast weakly motion with very small amplitude, and we have this very slow motion with large amplitude. The fast motion, which is the instantaneous response of the ion to the driving field, is called the micromotion. And the slow motion, which is the motion in the harmonic Tudor potential, this is called the secular motion. So this is really now coming back to the picture of Koehl. What he basically developed to understand the dynamics of the ion in the trap is sort of perfectly reproduced here. You have the ion that reacts instantaneously to the oscillating electric field. On top of that is confined to the harmonic Tudor potential and performs slow oscillation in that harmonic Tudor potential.
Is the micromotion only along X and Y?
In this two-dimensional trap, it's only along X and Y, yes. Okay, so now you may ask what we have learned in addition to our previous treatment. I mean, we could have guessed that already earlier. The thing that we have now understood additionally is that we can use Mathieu's equation to describe the motion of the ion. And if you look into the theory of Mathieu's equations, you will see that there exist either bounded solutions or unbounded solutions. Unbounded solutions are solutions where, when the ion starts on a small trajectory, after a while, the orbit goes to infinite radius. So then, in this case, the ion is lost from the trap. And for the bounded solutions, this means even at infinite time, the radius of the ion in its motion will be finite. And this can be analyzed mathematically, and you get these stability diagrams of the Mathieu equations, which are shown here in terms of the parameters A and Q. And you have to be sure that you operate your trap in one of these stability regimes. And this defines the correct frequency that you can choose to operate your trap. So here is the zoom in of the lowest stability diagram. You see here the beta parameter. If beta becomes 0, which are basically the two blue lines, then the trapping frequency goes to 0. Right? Beta was the proportional constant between the drive frequency and the secular frequency. This goes to 0, so then from that onwards there is no confinement anymore. And on the other hand, when the frequency of the drive becomes too fast, then we could also go to the regime where the trajectory of the ion is not stable, not because the potential becomes flat, but simply we cannot separate the scales anymore between the response of the ion, the micromotion, and the secular motion. And when these motions become coupled too strongly, then the Mathieu equations has no stable solution. So we're left to work in this regime, and usually one tries to work somewhere here near A equals 0 in rather small values of Q. And this defines sort of the parameters where you can operate the ion. Okay, so how does this look in practice? Here is the trap, sort of the schematic of the trap. On the big screen we see an ion trap that we built a few years ago, which is sort of one of these linear traps. And you can identify basically all the ingredients. You have these electrodes here, which are so U-shaped, for example, here or here. 4 of them, they compose these 4 RF electrodes. And then you have these 2 handicap electrodes at DC voltage. One is this thing here, you see the very front here, and the other one is that cone. And now if you supply some radio frequency signal to the RF electrodes, so in this case it was 250 volts or so at 40 megahertz drive frequency, and some small DC voltage, a few volts to the handicap electrodes, then you can trap the ions here in the middle. I should warn you, this is not an actual picture, this is photoshopped. So these are real ions, but sort of the scales don't match at all. So the gap between the electrodes here is 400 microns, and the spacing between the ions is on the order of 10 microns. Okay, so some more traps. How does this look like? Here is the very basic spherical trap, which is where the ion is all contained. So these are the 2 handicap electrodes. Here's the ring electrode. And so here's a penny in comparison of the ion is trapped right in the center. Here's a quadrupole trap, a big quadrupole trap. You see nicely the parabolic surfaces of these